I've never been, this is my first time to come to Evanston, but I have to say I have a lot of kinship with this place because in my time at Sandia and at Purdue, I've been always surrounded by a lot of really high quality people from Northwestern. Probably most notably Mike Forrestall, who I think a couple of you guys know, has really influenced me and my work, and not what I'm going to present today, but over the years he and I have worked together a lot and quite friendly. So just it's a real honor for me to be here, to be invited here to give a seminar, because I just have a really good impression of this. I hold this place in high esteem. So I've titled my talk in a way that I want to, show that I'm going to focus on the science, but the science is very much motivated by a very particular problem, and that's where I'm going to start. So first I'm going to show the importance of the problem, talk a little bit about some of the details that we're interested in capturing in our models, and then some of the efforts that we're making to be able to do this type of modeling. So there's the outline of my talk. So the motivation here, this is a picture of the natural gas production in the United States over the last 22 years. And you can see this sharp uptick in the mid-2000s, and this is just going to keep going. So another way to look at this is in picture. Look here at Texas. Obviously, this is a picture of the United States taken from a satellite at night. Look at the state of Texas. This bright light here is the city of Houston. That's the fourth largest city in the U.S. This is San Antonio here in Austin. San Antonio is the seventh largest city in the U.S. That's where I live. And you see this kind of crescent-shaped region here that extends south of San Antonio all the way into Mexico, that is lit up at the scale of these really large cities. Right? But if you've ever been that part of Texas, you know that no one lives there. This is ranches and farmland. So why is it so lit up? Here we are on the outskirts of Chicago. This is North Dakota. Nobody lives in North Dakota. I mean, there's less people in the whole state of North Dakota than there is in the city of Chicago, right? Yet the lights in North Dakota are on the scale of these really large cities. And if you know what else to look for out here in the Permian Basin in West Texas, and it's a little bit harder, but out here in the Marcellus Shale in Pennsylvania and upstate New York. So what's going on here? These are oil and gas plays driven by shale, driven by hydraulic fracturing. Okay? So the largest oil and gas play in the entire world right now is right here in South Texas. It's called the Eagle Ford Shale. There's about 22 counties in Texas where they're doing operations. They're going to drill 3,000 wells this year. They complete them with hydraulic fracturing. That costs somewhere between $3 and $5 million a well just to complete them. They're going to do 3,000 of them this year. They're spending a tremendous amount of money just to get the oil out. That gives you an idea of how much is coming out. One of the reasons the Eagle Ford Shale is hot, shale is typically associated with natural gas, but the Eagle Ford Shale actually has a lot of oil in it, and it's recovered in the same way through hydraulic fracturing. The 22 counties right there in South Texas are going to account for a gross regional product of about $120 billion over the next 10 years. Actually, by 2020, and so not next 10 years, in the next few years. $120 billion gross regional product. If you saw the numbers for November, the U.S. trade deficit is at its lowest point in 4 years right now. And that's because the most notable factor is because of oil imports. We're importing less oil right now than we ever have. Well, not ever have, but in any considerable time in history, because of what's happening right there in South Texas. So I'm trying to set the stage that what's going on here is a very big thing. It's improving a lot of people's lives, and it has an ability to affect all of our lives. So I mentioned shale. Shale is a sedimentary rock characterized by very low permeability. So on the scale, in petroleum engineering, they talk about permeability in units of millidarcy. Middle East reservoirs are out here at 100 millidarcy. Shale is way down here, so far less permeable than, say, concrete or granite. Okay, less permeable. It is permeable, however. Gas does travel through it. To give you some idea of how it travels through, one molecule of natural gas will migrate 1 meter in shale in a year. It takes 1 year for one molecule to move through shale. So you have to produce natural gas from these deposits, you have to hydraulically fracture them. Okay? So hydraulic fracturing is a process of initiating and propagating fractures by pressurized fluid. It's usually water. Most shales respond quite well to mostly water, about 98% water. But however, there's other things you can hydraulic fracture with. In fact, one of the new technologies is the hydraulic fracture with compressed natural gas, or liquid natural gas, rather. The benefit there is when you turn the well into production, you flow it back. There's not water in your natural gas. You put it right in the pipeline and you sell it. So there's a lot of new technology being invented. So the actual process is combined with horizontal drilling. So from a wellhead, they'll drill down. The Eagle Ford Shale in Texas starts at about 4,000 feet in the ground and goes to about 14,000. So you're talking about, a couple of miles in. So they go down about 2 miles and they'll go out. Sometimes a mile, sometimes 2. And then the actual process is that they go to the end. This is called the toe, and this is the heel, so it looks like a foot, right? So they go to the toe, and they perforate the wellbore. The wellbore has steel casing, so they poke holes in it, usually with shape-charged jets. They pump the fluid in at high pressure. It takes several hours to build up the pressure. Typical hydraulic fracturing will take multiple days to complete a well. So they build up the pressure, and they produce fractures. And then they move up the wellbore, they plug it off, and they do it again. They move up the wellbore, they plug it off, and they do it again. And sometimes they'll have, they call these individual portions stages. Sometimes a single wellbore might have as many as 100 stages. Typically it's probably like 30, okay? And the way that these stages are sequenced is very much the intuition of the fracture engineer. There's very little science that goes into it. This picture also serves as kind of the classic model of a hydraulic fracture. Long bi-wing planar fractures, okay? But I'm going to show you a picture in a minute that shows you a very different picture of what these hydraulic fractures actually look like. So, I know 30 years ago, Professor Keir and Achenbach, and I know Bazant, and a lot of guys here at Northwestern have been working on these problems and developing models that are relevant to these sort of long bi-wing planar fractures. I'm going to talk about natural fractures. So we know that the hydraulic fractures are influenced by natural fractures. We know this for a really long time. And if we go back, some of the most important experiments that were ever done in this regard were actually done by a guy named Norm Warpinski, who was at Sandia at the time. He worked in the geology group there. And they went to the Nevada test site out in Nevada, probably the only place in the world you could do an experiment like that. And they actually drilled an oil well, just like they would, right? They drilled 2,000 feet into the ground, and they did a hydraulic fracture. And then they used the tunnel complex at NTS to mine back to the fracture in situ. So there was tunnels already there. They mined back to them. That's why they call them the so-called mine back experiments. These are well known in petroleum engineering. And they mined back to them, and they got a picture of what the hydraulic fractures look like in situ. So this is pretty neat. And this is not a very good picture, unfortunately. I mean, I took it the best quality I could from the paper. It's sort of an older paper. But they have the schematic, and they show that from the wellbore you have it starts off as a bi-wing fracture, but this fracture interacts with a natural fracture in the rock. If you're a geologist, you might call that a joint or something. A natural fracture in the rock, and then it, pressure leaks off into this, fluid pressure leaked off into this natural fracture and produced a secondary fracture. So, fast forward many years, 2013, same author. He left Sandia in about 2000, started his own company called Pinnacle, which was later bought by Halliburton. So he works for Halliburton now. He's very well respected in this industry. This is a picture of microseismic events. All of those dots represent tiny earthquakes, okay, that were measured during a hydraulic fracturing event. This is actually 2 wells. So from one pad, they drill out and drill this first horizontal leg. You can see sort of a 2D view, but this is how long with respect to where, on the scale. These are feet here. Then from the same place, they drilled out and they drilled this. And this is becoming more common. In fact, this actually helps a lot with environmental concerns. There are a lot of traffic generated by these hydraulic fracturing events and stuff. And so if you can localize them, do it all in, set up one spot, set up an environmentally friendly place, contain any contamination, and do it all from one spot, it helps. And also kind of confines the road traffic and other things. And the oil companies can help build roads to those areas. Anyway, so now nowadays it's common to drill as many as 10 or 11, but maybe up to like 30 wells from one site. So these will be going out in radial directions all around, 30 of them. And so these are microseismic events. They're tiny earthquakes. They're about 1,000 times smaller than anything you can feel at the surface. But they're representative of natural fractures in the rock that are perturbed by stress perturbations when the hydraulic fracture is being conducted. The stress perturbations in the rock will perturb these natural fractures that are under pressure, right? Remember, it's 2 miles of earth sitting on top of them. And they'll slip, and they'll cause a little earthquake. They were monitored from this well here. And what we get with these, along with some other data, radioactive tracers and other things, is a picture of not long biwing planar fractures. If you do these experiments, these microseismic events, in a conventional reservoir where you do get long biwing planar fractures, these represent stages. So it's 1 stage, 2 stage, 3 stage, 4 stage, 5, 6 stages. The hydraulic fractures or the microseismic events will stack up along a stage. They'll be basically straight lines that come out. And here you see all this complexity. And that's due to perturbations in the stress, due to hydraulic fractures, due to leak off into natural fractures, creating subsequent fractures. And what you get is a very, very complex fracture network. Multiple biwing, multiple non-planar competing fractures propagating out into the rock, and sometimes competing with across wellbores. So you see seismic events on fractures way over here that were influenced because red corresponds to this stimulation, blue corresponds to this stimulation, or hydraulic fracture that was done here or here. So you have red way over here occurring near this wellbore when this was being done. So fluid is getting way over there and propagating fractures over in this region. So to solve this problem, this complex multi-fracture, multi-non-planar fracture, competing fracture network, at a reservoir scale, we need big computers because we're trying to track things that are a millimeter wide on a scale of a reservoir. And we need to know when they're, we need to be able to simulate and predict, influence of natural fractures across thousands of feet and be able to resolve things that are very small. So these types of simulations require big computers to solve. Some of the current modeling techniques, when I say current, I'm mostly talking about what's used in the industry, okay, not in academia. Pseudo 3D methods, they're essentially 2D boundary element type methods where the fracture height is basically implicit or used by an analytic model, accounted for through an analytic model. They use a lubrication model for the fluid in the plane of the fracture, and they use basically linear elastic fracture mechanics to add elements as the fracture propagates. And then they also use what they call a stress shadowing technique. So essentially these are analytic solutions that can give you some sense that there's another fracture nearby and influence the propagation of these. But what they can't do is account for any heterogeneity in the field. So when I say heterogeneity, and this is going to kind of an important thing, I'm talking about heterogeneity in natural fracture frequency and orientation. I'm talking about heterogeneity in material properties. I'm talking about heterogeneity in permeability and porosity of the rock. So, and when I material properties, I mean solid mechanics, strength of the material. And here's a study that was done by a colleague at UT Austin, Petroleum Engineering, where these are all common codes that are used by oil companies. So, obviously some of them are very explicit Marathon, right? They have their own code to predict hydraulic fracturing events. And what you see, I mean, which one is correct, right? They're vastly different predictions for the same. They were actually a set of experimental data that they were trying to compare to. So they were all given a set of parameters and asked to go predict or to predict it. And you see, fracture lengths on the difference of over 2,000 feet, half a mile difference in the predictions. And these are all basically pseudo 3D codes. Of course, there's some other methods. Your boundary element, discrete element methods, a company, Tasca, that has a code that uses that. And then in academia, we see some people using FEM and extended FEM. What's that? Well, this group here. So, Ted Blitzko. I mean, he's not here, so I don't see him at least. So these are some characteristics of the hydraulic fracturing model for the problem that I'm interested in solving. At reservoir scale, interaction, competing non-planar fractures, where they compete and they're influenced by other fractures at different stages and possibly different wells. So that's what I mean by reservoir scale. All right. So heterogeneity, I already talked about that a little bit. Non-planar fracture models, fluid mechanics, and heterogeneity here. And this is sort of what I'm going to focus on. But my group, we're working in all these areas. And then other, some kind of practical aspects. So we're interested in building realizations of very stratified, complex geology. And if we have tools that make it easy for us to do that. So we're talking about meshing. You might have tight pinch outs in geology. And if you need to mesh that with traditional finite elements, can become difficult and other things. And computational efficiency is certainly a relative word. What's computational efficient to me after spending 7 years at Sandia is not computationally efficient to someone in the oil industry. I can tolerate simulations that take a week on 1,000 processors. A guy at an oil company cannot. He wants an answer in a few hours and at most maybe one day. So I'm going to dig in on the modeling a little bit to show you that a model we developed to handle diffusion in this heterogeneous media, it's a non-local model. And the non-locality comes from heterogeneity that we're going to exclude. So there's multiple types of heterogeneity. There's really small heterogeneity, small fluctuations in permeability, possibly micro cracks that fluid's going to flow through. And we're going to exclude those, right? And that's where non-locality comes in. But then there's large heterogeneity. There's large heterogeneity, things we want to see. We want to see the major faults, the big fractures. We want to see large changes or discontinuities in diffusion across large stratified geology. Okay, so we're going to develop a non-local model. Show you how I developed that. We're going to start with the classic, diffusion equations, Fick's law, and just because I want to get it out of the way, because I'm not really going to do anything with it, it's going to be along for the ride. If this term over here you can think of as a source term, and this is a sink of a diffusing concentration U away from a point X. Well, I'm just going to accumulate those together. So I'm going to move that over there, create a new variable f of x, and put it over there. And then I'm going to develop the variational problem. Okay, so this is just, if you're a finite element guy, this is a weak form. This is very standard. I'm going to multiply through by the virtual variation in U. I'm going to integrate by parts, shifting some of the differentiation onto the virtual variation, and therefore weakening the continuity requirement of U. And this is the so-called variational problem, okay, where you have a bilinear function and some forcing term. All right? I'm going to exploit the bilinear nature of that first term, being that I can replace either of its arguments with itself and then just pull a 1/2 out here. And if I do that, then I can pull, and the fact that it's bilinear, I can pull the del operator outside. And then from that, I can infer a quadratic functional. Okay? So this is a quadratic functional of that diffusion, classic diffusion equation. A lot of people in the kind of this community aren't used to seeing this. If you're a finite element guy or solid mechanician, this is just, the analogy is a potential energy function. We're all used to seeing this, right? My colleagues, when I was working on this and showed them this, they'd never seen it, so I had to work through the development. All right? So I'm going to take this term. This is the one we care about. I'm just going to call it Z. All right? You might call it a flow potential, if you will. All right? Z, and so I'm just calling that Z, and I'm going to put it there. Now remember, U has a continuity requirement here. Okay? So U is local to X. It depends only on X, and derivatives of X must exist for this equation to be valid. And I want to remove those restrictions. So I'm going to remove locality. I'm going to say, okay, now I have a new Z, I call Z bar. It's not just dependent on X. It can be dependent on points remote from X. And I'm going to remove the continuity requirement. So I'm not going to say that derivatives have to exist, because the diffusing concentration across an interface of from one region of one permeability to another is going to be a discontinuity in the diffusion equation. I mean, in the diffusing concentration. And so when I remove those restrictions, and this is just some notation, U is a function of X prime, and I might write that U prime. And then I might just say that Z is a function of U prime minus U and X prime minus X. And then I might replace U prime minus U with this thing I'm going to call a diffusion state, if you will. This is just some notation. And if I need to disambiguate, I might use this notation just to say that this diffusion state is associated with this vector, X prime minus X. Okay? And I'm going to go the other way. I'm going to minimize that quadratic functional now with my new Z that I've removed the continuity requirement on. So I minimize the quadratic functional. And when I do this, this is what I want to bring attention to. Because of this function space that Z now lives in, because I've removed the continuity requirement on it, you get this term in solving for the first variation of this Z. This is an inner product of on this function spaces of the Frechet derivative of Z and the first variation in U. So this new integral pops in. That's an integral over x prime. Okay? And then I'm just going to manipulate it a little bit further, and I get this equation. Of course, I has a stationary value when the first variation of I is equivalent to 0. So then for arbitrary variation in U, this term here in parentheses has to be 0. And so that's what I have here. I'm just going to replace the notation. So I'm going to say that Q, which I'll call a flow state, if just to give it a name, is a Frechet derivative of Z. And then I'm going to undo what I did earlier. And now I have this as my non-local diffusion equation. Okay? So 2 observations on my non-local diffusion equation. The first one is, in the local limit, when my non-locality shrinks to nothing, I can recover the classical model. So Q is essentially the constitutive response of the material. Okay? So if I propose the constitutive model to be a diffusion tensor, D times, here I'm approximating the gradient using a moving least squared approximation. I could show that this approximation is exact for linear profile in U. And so if I plug this in, and then I'm going to say that it's 0 outside of some length scale delta. So whenever that x prime minus x, whenever it's smaller than delta, larger than delta, it's 0. There's no influence. Okay? So I'm going to use that constitutive model. I'm going to Taylor expand the gradient of U. Okay? I'm sorry, U at x prime, about the point U at x prime equal x. Because again, I'm interested in seeing what happens when non-locality goes to 0. So x prime is a point remote from x. And I have x, and I'm going to shrink them. Right? So I'm going to Taylor expand about that point, and then it's just plug and chug. And I know there's a lot of equations for a slide. I plan on making these slides available if you want to check me. But it's just ij's and k's. You plug it in, and you start working through this integrand. We exploit an anti-symmetry. There's an anti-symmetry here, so that term goes to 0. And you go, 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 and eventually you end up with this, plus some term that's on the order of delta. And of course, as delta goes to 0, you recover the classical diffusion equation for constant D. Okay. Now, it's not much more difficult to actually show the same thing for non-constant D. You have to do another Taylor series expansion about D at x prime, but that's far too much math for one slide. So that's one observation. In the local limit, our non-local diffusion equation recovers the local model. Okay. Another observation, if I choose Q, again, this is a constitutive model, to look like this, okay, where C is a scaling constant. And the scaling constant depends on, this is a gamma function, it depends on, N is the degree of the 1 dimension, 2 dimension, 3 dimensions, right? The dimension of the problem. And S is something I'll call a fractional order. If I plug that in and plug and chug, the right-hand side, with all those integrals, become this. And this is pretty significant because that, I don't know if you're familiar with this literature, but that is identical to the fractional Laplacian operator. And if you go to the literature, say water resources management or people that do hydrology or do soil mechanics, this is the standard way to do anomalous diffusion. So when you have fractured aquifers, for instance, Darcy-Fixed law, you can't model diffusion in that environment, right? Unless you actually model every tiny little crack, right? And you go to that scale. They don't do that. You exclude that, and it results in a non-local model. They use a different model than me. They use fractional Laplacian, but the model that we've developed here shows that the fractional Laplacian is a special case. And the real way you show this is in the Fourier transform. You take a Fourier transform of that, take a Fourier transform of that, they're the same. So everything I've done up to now is just math. I wanted to strip off all the units to not complicate things, but now I'm going to put the units back in and we're going to do some engineering. So this is just the same equation, The classical mass transport, fluid transport in a porous media. This is flux here, this Darcy's law. So you have this is only valid for small compressibility C, the fluid density rho, and viscosity mu. This is a permeability tensor. So the non-local equivalent to that, all the details are in this paper. The non-local equivalent to that is this here with, yes, sir?
So if I want to account for higher velocity, that means you account for the transport.
Yeah,
Would this work?
higher velocity, not as it's written. Higher velocity, you'd use like a Furker equation, which would have the flux would be dependent on a velocity over here. As it's written here, it's not modified to do that, but there's nothing there. Oh, to do advection diffusion, we could do the same thing. We could develop a non-local model for that. So we come up with the actual parameters from this by basically doing the same thing. We come up with a generic constitutive model with some scaling functions, and we let it go to 0 so that it approaches the non-local model, it approaches the local model in the local limit, and that's how we parameterize this. But this is the standard local diffusion tensor. And one thing you'll interest, there's no derivatives here, right? This is the pressure at point x prime and the pressure at x, and there's no derivatives. I didn't make no assumption on continuity.
So if you have shocks,
Yes,
would this work?
I think so.
But you have a jump.
Yeah, I'll actually show you. I'll show you an example. No. I'll show you an example in a minute where I have a sharp discontinuity in pressure. Yes, sir.
Is the motivation to develop the local model from the numerical side or from the underlying physics side?
Well, it's from the underlying physics, but there is some convenience on the numerical side as well. I'll talk about that in a minute. But the physics are, and it comes from, again, motivated by all of this work that's being done on anomalous diffusion in fractured aquifers and other things. We're not going to, we definitely want to see large fractures, right? But we're not going to model every tiny little microcrack that's in the media. And those smaller fractures that we're going to exclude, we're going to make the modeling decision to look at them from a bigger lens and exclude them from a model. But they cause non-locality. They cause anomalous diffusion.
Microcurrents are important for escape of the gas.
For what?
For escape of the gas. What is
They have to.
of the correction
The microcracks have to be conductive to the main fracture. There has to be a pathway, and I'll talk about this in a minute. I don't really get into the details here, but it's not enough to produce a hydraulic fracture. If you just pump water in and you stop, you have 2 miles of earth sitting on top of that crack, it's going to close and it won't produce. This is done, right? I mean, they know this. Pump water in, you create the hydraulic fractures, you stop, it flows nothing to the surface. You have to make them conductive, and the way you make them conductive is you pump in a proppant, which is typically a sand. And it's not a sand like you go to the beach. It's a very fine screened sand. There's also some artificial materials that they pump in. And the sand not only has to be pumped in, but it has to be controlled. So say you have an oil reservoir. So you pump in sand, now you're propping the crack open, and you flow it back. Well, the sand's just going to flow back in with the oil, and you have to do it over again. So they have to pump the sand in, they have to hold it there.
So the gas is trapped in nanopores.
They're trapped in nanopores, but those nanopores have to be fractured such that they're conductive to a main fracture that's propped open so that it can travel back to the surface. It will never get there. Exactly. Yeah. We're excluding them from the model, but they're implicit in the non-locality because they cause dispersion.
So the real challenge is that you have a continuum model.
Yes.
Right? And all the processes you're talking about here are below the scale that resolve in a continuum model.
Yes.
So how do you relate the continuum properties to the scales you're explicitly resolving? Because that coupling is really critical in establishing that continuity.
That's a hard question.
I know.
And I wish I could say you go to the lab and you do these 3 experiments. It comes in the length scale of the non-locality partially.
Right.
And you know, I get this question a lot because I have an integral, and there's my length scale. And so people say, well, how do you come up with that? But I never read the fractional Laplacian. I never say, well, where do you come up with the fractional order? Because it's the same thing. The fractional order determines the length scale. I've never heard anyone, and maybe people don't understand it well enough, but I've never heard anyone say, how do you determine that fractional order from the material properties? It's fit. It's fit.
Yes.
So
Same thing here.
in theory, you can take your delta small enough to look at all the details. So that's a large scale problem. You
No,
know.
but
But I think I'll let the speaker keep a finish, and we have 15 minutes
Yeah.
to Q&A. Okay?
Okay. So I want to solve a validation problem. My colleagues are petroleum engineers. I work with them, on this, and this is a problem that they wanted to solve. So this is a common problem in petroleum engineering. Say in the Middle East, where you have the real estate, this is how they would set up a petroleum reservoir field. They would drill vertical wells now, not horizontal, in a 5-spot pattern like this, such that you have producers and injectors. So the injectors inject fluid, and the fluid diffuses through the media, and it's produced there. And then they use a separation process to get the oil out. So they
Use green for producer. That's my.
well, that's a good point. So in the interior here, if we look at the interior, well, then we can use symmetric boundary conditions along the edge, and we can only look at this kind of one block. So we use symmetry boundary conditions along the edge. There, turns out there's an analytic solution, an analytic local solution. One of the problems with these non-local models is hard to get analytic solutions, very hard. It's a very small class of problems that you can do that for. So typically when we code it up, we want to verify if we coded it right. So we have to go back to the local solutions to do that, the analytic local solution. So there's an analytic classical solution of this problem. So this is the pressure. This is a pressure across the diagonal here. There's an analytic solution to that. And if we coded our non-local model and we shrink the horizon, or what I'm going to call the non-locality, we shrink it to nothing, then you can recover the local model. So we coded it up good. But here's another interesting feature of the non-local model. If I take a block and I just stick it in there, zero permeability. So you have a regular porous media out here, and you have an impermeable region right there. And I solve the same problem. I don't change a thing, except putting in the material properties where there's zero permeability, zero, and where there's another permeability value. Without any interface condition at all, I recover. You can see the sharp discontinuity. So you see this is pressure along this axis now. So the pressure, and then it instantly drops to zero along the boundaries of that. And it's too much math to show, but we can actually show that this non-local model, the two-domain non-local model, converges to the two-domain local model and the interface condition, and the boundary condition. The boundary condition is implicit in the non-local model. So the boundary condition is continuity of flux. It would be a continuity of flux across this interface right here. So this is how we can, with this non-local model, capture large-scale heterogeneity. Okay? So large-scale heterogeneity would be large things that we're not excluding now. Okay? So we want to capture a discontinuity and diffusion across this interface because it's large. It's a large stratified geology or whatever. Okay. Briefly on the solid mechanics, we have a very similar formulation for the solid mechanics model. We start with a Hamiltonian, again, where we have a strain energy density functional that is not dependent on gradients. Okay? It's dependent on the true deformation of x prime and x. And the Euler-Lagrange equation associated with this is this equation, sometimes called the parodynamic equation. And what you have is where this t is a Fouché derivative of the strain energy density functional. So this can be derived from a variational principle. Examples, you've probably seen some of this work. Some of this is I did at Sandia. This is a rigid plate and a concrete sphere, and the concrete impacts the plate, and you get massive fragmentation, and these mean fragment sizes agree well with experiment. This is some ductile failure. This is the work I used to do at Sandia on penetration mechanics. So here we're investigating the effects of having an interface between two targets and comparing that with a monolithic target, because we want to do some experiments on large-scale pieces of concrete. So here we have basically two targets. The projectile impacts into one. Those color contours are contours of damage. And you can see that the cracks sort of arrest in the first target momentarily, and then they propagate out ahead. into the second target. And this is consistent with what we saw in experiments. And then I show you this. You don't see the impactor, but this is like a ball impacting a rigid plate, and you get this complex fracture patterns. And I show you this because these are the complex, this is the type of fractures that we're chasing after in these hydraulic fracture events. So this is a fracture model I developed for this theory. So this theory you can think of like a continuum version of molecular dynamics, okay? So every two pair of points, x and x prime, have some force density associated with it. And I have it drawn here like this, but in general, these forces don't have to be along the plane of action, and they certainly don't have to be equal and opposite. They're not springs. If they were, then you're restricted to quarter Poisson ratio in 3D and other things that lattice models have. So the forces are not equal and opposite, but there's a force density associated with it. And so because we can define a force density associated with each pair of points, x and x prime, when we displace those points, there's work done that's associated with that bond. It's an energy density, okay? So if we integrate this over time, then we have some energy density. The units of this are energy per unit volume squared, okay? So we can track this over time and calculate the work that's continually done by displacing those points. And if we consider this, so if we consider a point A that lies along this line that goes from 0 to out to some length scale delta, and all points B within this spherical cap. And this is in 3 dimensions, and the surface there is of unit area. So the surface that's being cut here is of unit area. If I assume that every point A and every point B has some critical energy that at some point, for some reason, will be irreversibly removed or broken, if you will. Okay? So it has some critical energy. Okay? Well, the total energy, if I integrate all that up between all interactions B and all interactions A, what that is the total potential energy required to open up a new surface of unit area, or the strain energy release rate. Okay? So if I compute this integral, putting WC in there, compute this integral and equate it with G, I can solve for this critical energy of a single interaction in terms of a fracture mechanics parameter. Okay? So then, of course, if you want to do plane strain fracture toughness, if you have a plane strain, you can plug it in and use fracture toughness instead of strain energy release rate, and therefore we have a way to define how much work can be done on a bond before it will fail, a bond being a point A and B. I don't like that word bond because it seems like a spring, but it's... Yeah.
So if you really look at the real problem, you have 2 miles of curve sitting on it, so you have a lot of initial stress. How we change
So what I'm going to show you today, I don't believe is the right model. It's not the right failure model. It's not the, we were using linear elasticity, which, by the way, everyone in the petroleum engineering uses. I don't think it's good enough. We need pressure-dependent material models. We need more complex fracture mechanics. We need fracture models that can predict competing fractures when you have large process zones that interact with each other. This is just a model for proof of concept that I'm going to show you today. Okay? This model actually has been compared with experiments for metals, and it works really well, where linear elastic fracture mechanics applies. Okay? So here's the constitutive model. This constitutive model recovers linear elasticity in the local limit. This term is an isotropic term. I can refer you to the paper to get all the details. This is like a deviatoric term. Those are your regular old bulk modulus and shear modulus. Again, I don't believe that this is sufficient enough to model rock. We have to use more complex constitutive models, but we're just sort of in the beginning phases of this work. But we're going to modify it in a bio-poroelasticity fashion. So we have a dilatation term that we're going to add the pressure that's solved in the fluid mechanics problem, the nonlocal fluid mechanics problem I showed you earlier, multiplied by a BO parameter. Okay, this is standard. What it results in is something that's very analogous to standard BO poroelasticity. And then, of course, when I add this additional pore pressure, it might cause additional work to be done, and those interactions might fail, causing some failure. And we can characterize that failure through a scalar damage variable, which is basically the volume fraction of intact interactions. Okay, so the ones that aren't failed, or the ones that failed, rather, the interactions that have been removed. So one way to think of it is in a discrete setting. If you had 100 points that were interacting and you removed one, you have 1% damage. Okay? Now, damage doesn't necessarily mean there's a crack there. Cracks occur through the coalescence of damage in a natural way. Okay, so we're going to modify the permeability tensor in the damaged regions. And right now, we're using just this linear modification. Again, this is an area of research. I think we're going to have to go to experiments. And I mean, this is an empirical model. We're going to have to use experiments. We're going to have to use higher fidelity simulations of small-scale cracking and the fluid flow and small cracking to get this correct. The discretization is kind of easy. We replace those integrals with sums in a discrete setting. It results in a particle method. We've, in some work that I've done with one of Professor Liu's students and Professor Belichko and Professor Liu, we've actually shown that discretization for the solid mechanics, under certain assumptions, relates back to or is equivalent to the classical mesh-free discretizations under certain assumptions, namely continuity in the displacements, which I removed that restriction initially. But if we make that assumption and then say first-order polynomials in RKPM, you can show that they're identical. This method is currently implemented in these codes, DOE codes. I've worked on all of these. I have code that I wrote in all of the distributions of all of these codes. Most recently, I'm working on this code, which I'll talk about later. Let's show an example. This is a an anisotropic permeability. So this is the contours of pressure on the left, damage on the right. So this is, you see fluid pressure here, pore pressure, and you see basically a crack propagation there. And this is an anisotropic permeability field. So the preferential orientation of the fluid flow is in this direction. And you can see that it drives the crack. So I have nothing on the crack tip telling it to go in that direction. It's the preference of the fluid to flow in that direction that's turning the crack.
Is this a couple?
It is coupled. This is an isotropic permeability field, and you can see that in the pressure. It diffuses isotropically. But then what you see that when the crack initiates, when the pressure drops, it's because it's driving the crack out. And these are representative of natural fractures. So these are discontinuities in the solid media already. And here you can see that the crack grows out. Again, if they weren't there, the crack would just go straight in two directions because it's an isotropic field. The crack drives out and intercepts this natural fracture, grows along it for some time, and then continues on.
Don't they branch?
In this model, do what?
Under pressure they must branch.
In this particular model, it's actually not that. The material properties in this example aren't physical to shale, so I don't see any branching, but they could. I don't see it here.
The calculations they do branch, which is really.
So I do have a simulation that shows some branching, but not in my simulation here. So just showing here, a typical actually perforation where they perforate the steel casing is done in multiple directions, and there's no way a priori to know exactly which crack will dominate. It's dependent upon the field. And so here you see there's initially like 4 perforations and then these kind of multiple cracks. One of them goes out, intercepts a natural fracture and grows along it, and these are influenced. And again, there's nothing turning these cracks other than the preference, the interaction with the natural fractures and the fluid flow. I'm not telling the crack where to go in any way.
Is the fluid pressure everywhere on the crack that penetrated, or is it just in the fluid?
Well, this is fluid pressure here. Okay, so you can see it's highest here, but it's not getting all the way to the crack tip.
Okay, so it depends on time.
Okay, so those were 2D simulations done in a small scale code, like a prototyping code we use in my lab. We're in the process right now. The theory is fully developed for 3 dimensions of putting this into our large scale code paradigm, which is built on top of Trilinos. This is this code distributed by Sandia National Labs. I've worked on it since I worked there, and I think I'm the only non-Sandia developer for it now, with access to the repository and everything. So the great thing about it, this is a really high quality, production quality code. It scales excellent. I've run this on thousands of processors and got excellent scaling. And the real cherry here is being able to use Trilinos and all the solvers that come with it, all the nonlinear solvers, nonlinear conjugate gradient, all this. It's going to allow us to put more physics in and still be able to get solutions. I just acknowledge, I talked a little bit about it already, but ultimately we want to go to multi-phase fluids, so we want to be able to include other chemistry that's in the fractured fluid itself. We want to be able to look at oil, gas, condensate in the solid media and be able to see how it's transporting, as well as contaminant transport to do the environmental studies. We need to look at slurry transport. So slurry transport is going to have a viscosity that's a function of the pressure differences as well. This is how we're going to do that proppant modeling. Because again, without proppant, it doesn't matter. You can produce all the fractures in the world. If you don't hold them open so that they're conductive to the wellbore, you didn't do anything. Okay? So we need better fracture mechanics. We need fracture mechanics that can, where we have large process zones. Professor Bazan's actually taught me so much about, the process zones associated with long, stable cracks and everything, with all these microfractures that cause these very, very large length scales. And of course, when you have multiple cracks, they interact with each other. All the energy is not dumping into creating a single crack. It's creating multiple cracks, and I think we need to improve the fracture mechanics there. I'll just skip the HPC stuff, but we're looking at using new architecture, hybrid parallelization to get faster and faster simulations. This work is funded by National Energy Technology Lab with joint funding or matching funds from this hydraulic fracturing and sand control. This is how important the sand is. They even named the Joint Energy Program hydraulic fracturing and sand control. This has 28 industry companies, everybody who's anybody, Exxon, Mobil, Shell, all the service companies, Halliburton, and I'm a member of that and tied in with those guys. So, opportunities for collaboration here. I see quite a few. All of the great people in the TAM group can help me do some better fracture mechanics, and we needed more physics, pressure-dependent materials, and other things. Proppant design. I think there's a lot of work to be done here. So we need to have proppant that can fill the crack and travels well in the crack, but doesn't cake it up. And material science, we can use synthetic proppants. Work with the Northwestern Argonne Institute in a number of ways. And then I hadn't really talked about it, but there's a number of uncertainty quantification that we need to do based on frequency and orientation of natural fractures and other heterogeneities. Okay, I do some other research real quickly. This is just a large-scale computation. This is many millions of degrees of freedom. Run-in paradigm. This is a cylindrical compression. This is a copper ring compressing sand. And the color contours there are damage. That's not continuum damage. That's discrete fractures. So we're modeling thousands and thousands of discrete fractures, and the simulation is holding together and running. So this is just an example of large-scale fracture. I do this work with Sandia. They do the experiments. I do some simulations. I have some other funded research. I work in a Muri Center where we're doing constitutive failure modeling. Some HPC is my tasks. I do some non-local beam plate shell theory. This is actually my Young Investigator Award project. I do some work with ARL. There's my research group, minus one guy that I didn't get a picture of. And I sped through the last part because I really think this is important. These are the courses I teach, on record. These are the courses I've taught. But I want to talk about how I teach this high-performance computing class. So I flipped the classroom. There's a lot of talk about flipped classroom, right? So what I do, I've recorded about 60 lectures on these high-performance computing topics. Everything from the first day, we start with LS, because these guys have never seen a command line. By the end of the course, they're writing parallel programs using MPI. Not only MPI, but they're using Trilinos. I don't know of another course at a university anywhere where they're using Trilinos, which is basically a production quality high-performance computing library, okay? And the way it's conducted, I didn't know if I'd have internet access here, so I just recorded a video of me playing around with it. But basically, I've recorded these lectures. They're about 10 minutes in length, usually. The students go and they watch the lectures before they come to class. I enforce that they do that through a quiz system that I've set up. And so I'm just recording myself playing around here. You'll see a student will be logged in. A quiz will be generated from a question bank here. They watch the video. And then when they're done, they take the quiz. Now the video is a combination of me talking and annotating slides, but more importantly in this setting, high performance computing, eventually I'll speed along here and get to, so I'm just fast forwarding the video to get to the point where, so again it's a combination of me talking and annotating slides, and eventually I'll get to the point where I'll flip over to the terminal and I'll actually work examples. So just a little bit further there. Okay, so now I'm working examples in the command line, and they get that example. Then what happens is they come to class. Class is taught in a computer lab. We all log into a supercomputer, little supercomputer, 200 cores, on campus, and every class we write a program. Every single class, 25 programs in one semester, plus some projects. Their final project is to solve Laplace's equation. 25, but the beauty is I'm there to help them. This is basically their homework, right? They come in, I have an assignment at the beginning of class, they get started on it, and they get stuck, and I help them through it, okay? And then they have some projects. The final project in this class is actually to solve Laplace's equation in parallel using this Trilinos massively parallel library. and undergraduates do it. They do it, and so this class is really taken off. It's packed. It's full every semester. Only limited by the number of seats in the computer lab because of the way it's taught. And here's the
Another thing, if they bring their own computer.
they can use that. And in fact, I encourage it. Yeah. So if you got a Mac or Linux box, it's really natural just to log in. So this is an unintended consequence. When I set out to do this, I was actually thinking, well, it'd be a lot of work up front, but once I do it, then it'll teach itself, and I can get back to doing research. Right? That was my thought up front, but this is the unintended consequence. I post those videos completely openly to YouTube, so that I can go to YouTube and I can look at who's watching. And this is the neatest thing to me. So it's kind of hard to see, but right here it says YouTube embedded player. That's the people watching the videos from my website. And that's only 14% of the total people watching. So over 41,000 views are coming from people I know aren't my students. They're all over the world. I have, to date, in a year and a half, 51,000 views. I mean, this is not a lot for, like, compare it to some dancing cat or something on the internet. But for a highly technical Trilinos parallel programming library, right, this is a lot of views, right? 214,000 minutes. And of course, you can pull up a map of the world. Countries I never heard of, students or people are watching these videos, and I think it's really cool. And so here's the unintended consequence, is that it's established my reputation as an authority on this subject matter, and I get emails all the time about how do you do this, how do you do this. And so the teaching has brought people to me for research. And I think it's really kind of neat. And I didn't have this master plan. It's just happened that way. And in fact, the Sandia guys got wind of it, and now the Trilinos developers, and you got to remember, Trilinos is one of the core, the biggest things, R&D 100 winner, all this. I mean, it's something Sandia is really proud of. Now they're going to start using my videos as tutorial content on their website, and I think that's really cool. So, with that, I'll take any questions.